So next one, now we have angular frequency and time period as omega f and t. So angular frequency of velocity is the same, acceleration also have the same, but angular frequency of the kinetic energy is double as the function cos square. Let's say the cos square omega t can be simplified as 1 plus cos 2 omega t by 2. So here you can see that angular frequency is 2 omega. So for kinetic energy it is 2 omega. Similarly for potential energy it is also 2 omega, because potential energy involves sine square, which can be simplified as 1 minus cos square omega t, which can further be expressed in terms of 2 omega t. Now angular frequency of mechanical energy. So mechanical energy does not change itself, so its angular frequency is 0. Next is time period of velocities. So frequency is same, so time period of velocity will be same as that of t. Then we have time period for acceleration. So time period for acceleration will also be same as that of t. So first is correct over here. Then we have time period of kinetic energy. So obviously frequency gets doubled, so time period will be halved. So it will be given by t by 2. Next we have time period of potential energy. It will also be t by 2. Next we have time period of mechanical energy. It will be infinity as omega is 0 over here. Next is frequency of velocity, same as that of f. Next, frequency of acceleration, same as f. Frequency of kinetic energy, double. It will also be double. Mechanical energy has frequency 0 as it is constant. Next is a particle executes shm as given by this: kinetic energy as a function of axis. So velocity here will be, we can use the equation that v is equal to omega root a square minus x square, or we can use verification techniques that if x is 0, which corresponds to the mean position, so kinetic energy will be maximum over here, which is given by the second option. Next is graphical variation of kinetic energy. So it will be a parabola, and in fact this graph should be like this. So just shift this graph to this, it will be like this. So fourth will be the best option over here. Next is graphical variation of kinetic energy with x square. So assume that x square is equal to y. So kinetic energy can be written as c minus ky, k dash y, which is a straight line with negative slope. So it will correspond to option number 4. Next is, if potential energy at mean position is u0, then potential energy as a function of axis. So it is given by the first option. Next is graphical variation, second आ जाएगा parabolic, and initial value is u0. Next is mechanical energy. So mechanical energy remains constant with respect to x. So it will correspond to option 1. Next is kinetic energy of the particle executing SHM is maximum at. So it is maximum at mean position. Minimum at, so it is minimum at the extreme position. Next is potential energy of the particle executing SHM is maximum at. So it is maximum at both left and right extremes. So both will be correct over here. Next is potential energy is minimum at. Next is potential energy of the particle executing SHM is minimum at. So it is minimum at the mean position. Next is mechanical energy of the particle is maximum. So mechanical energy is a constant. So it is same at every place. So fourth is correct over here. Next is concept of potential energy is possible only for. So it is possible only for conservative forces because potential energy refers to the energy which can be brought back to the system and it is in between the constituents of the system. So when non-conservative forces are there, that energy gets dissipated in terms of heat or sound, and it is not possible to bring them back within the system itself. So this concept is only possible for conservative forces. Next is the total mechanical energy of a harmonic oscillator is. So total mechanical energy remains constant and it is independent of time. Next is a linear harmonic oscillator possess an element of springness and an element of inertia. So this springness is concerned with, so obviously spring is concerned with potential energy and that inertia or mass is concerned with the kinetic energy. Next is in a linear harmonic oscillator kinetic energy peak once during a time period. Obviously the time period is half, so it peaked twice during a time period corresponding to the position of the particle. So second will be correct over here. In a linear harmonic oscillator kinetic here we are being given the graphs of that. So we are being asked the amplitude of the SHM. So obviously origin is taken at the mean position. So we can see that kinetic energy is minimum at x is equal to 2. So it's gonna be the amplitude which is 2 meter. Next is distance traveled by particle in one complete oscillation. This is 4a. So 4 into 2 will be 8 meter. Next is time period of oscillation is. So here for finding time period we can see that maximum kinetic energy which is half ma square omega square, it is 20. So here m is 2 and if we substitute the value omega comes out to be root 5. So time period will be 2 pi by root 5. So it will correspond to first option. Frequency is 1 by t, it will also be correspond to first option. Next angular frequency is root 5. Now position of P is, so at P you can see that both energy coincides, it is a by root 2, so which